Picture a fossil hunter standing in the cracked red badlands of the Moroccan Sahara. They are brushing sand off a row of bones that should not exist in a place this dry. It was a tail, but built completely differently than any dinosaur tail found before it. It had tall, blade-like spines, longer than a person's arm, curving into a flat, deep, and flexible shape that functioned almost like a giant paddle. To understand why it looked like that, you have to look at the environment those bones came from. During the Cretaceous period, this arid desert was a sprawling, churning river system, completely soaked in water and crawling with massive prey. These waters were packed with dangerous meals. You had coelacanths the size of a grown person and giant sawfish moving through the currents with snouts full of barbs. You don't snatch a person-sized fish by dipping a toe in from the bank. A predator that wanted to survive off this hyper-aggressive menu had to commit to the water in a serious way. That brings us to Spinosaurus. This was a 50-foot monster with a giant sail rising off its back and a long, narrow snout packed with interlocking, cone-shaped teeth, almost exactly like a modern crocodile. The anatomy points heavily toward the water, but the moment you ask exactly how it hunted, you hit a wall. Right now, there are 2 rooms full of brilliant scientists staring at the exact same bones and walking away certain the other side is wrong. One camp looks at the skeleton and sees a deep water swimmer that chased down prey like a great white shark. The other camp sees an animal that waded lazily at the shoreline, never fully submerging. The inability to cleanly answer how deep it went has ignited one of the loudest, most stubborn scientific arguments of the last decade. In 2020, the swimmer hypothesis gained massive ground. A team described the most complete Spinosaurus tail ever found in Morocco, and to prove how it worked, they built a robotic model and tested it in a water flume. This chart shows the results. When they measured the forward thrust generated by that flexible, fin-like tail, it produced 8 times the power in water than the stiff tails of traditional land-bound theropods like Allosaurus. 2 years later, a separate team analyzed cross-sections of femur and rib bones from 250 different species to build a massive data set on bone density. They were looking for a specific biological signature. Animals that spend their lives underwater require dense, compact bones to act as a diver's weight belt. It fights buoyancy and lets a heavy body sink instead of bobbing at the surface. This rule applies across the board, from manatees to penguins. And when they checked Spinosaurus, the bones came back fully dense. Between the mechanical advantage of a hot frost tail and the biological weight belt of dense bones, the swimmer camp had built an incredibly compelling picture of a deep-water torpedo. But the opposing camp looked at those exact same features and ran their own numbers. They built a precise 3D biomechanical model of the dinosaur to test what it could actually do in virtual water. First, they examined the structure of the tail spines. Real aquatic predators have narrow, spool-shaped vertebrae that allow their tails to whip with power. Spinosaurus had blocky, squarish bones, which would make the tail behave more like a floppy billboard waving in the water rather than a precision propeller. This graph illustrates the resulting speed calculations. Fully submerged, the model hit a maximum speed of about 1.4 meters per second. That is a full order of magnitude slower than modern aquatic pursuit predators. It simply couldn't catch fish in open water. Diving math was worse. Pushing the animal underwater required 15 to 25 times more downward force than the tail generated. Floating at the surface, the sail caught the wind. The model was highly unstable, rolling onto its side like a capsized boat. As for the dense bones, the skeptics argued they weren't a diving weight belt at all. They pointed out that massive, heavy land dinosaurs develop thickened, infilled leg bones simply for the structural support required to walk on land without collapsing. The cold math of flotation and drag violently strips away the image of a sleek, diving torpedo, replacing it with a heavy, unstable animal that would struggle to swim at all. If it couldn't swim, but it clearly ate fish, there has to be a middle ground. Paleontologist Paul Sereno proposed a compromise model that respects the physics without ignoring the river habitat. Instead of a swimmer, picture a wader. The dinosaur walks into the river on short, powerful legs until the water is about 6 feet deep. Then it stops. It plants its toes firmly in the mud and waits to ambush any fish that drifts too close to those crocodile jaws. In this scenario, heavy bones provide the essential stability needed to withstand strong river currents while standing in deep water. It's still a terrifying 50-foot shoreline trap. It just hunts from a grounded stance instead of pursuing its meals into the deep. The reason we have to rely on physics models and statistical debates to sort this out is a matter of terrible historical luck. The fossils we have are frustratingly incomplete. The best original Spinosaurus skeleton ever discovered was completely destroyed during a World War II bombing raid in Munich. We are rebuilding this animal from scattered fragments. Each new find forces an update to the model, refining the picture as the evidence gets sharper. You've weighed the tail thrust data, the physics of buoyancy, and the density of the skeleton. Now declare your verdict in the comments. Do you believe the animal was a deep diver or a shoreline wader? Spinosaurus remains a work in progress, a prehistoric giant being rediscovered in real time as the evidence continues to evolve.